Now this week we are going to study a radial heat conduction. What is meant by radial? In linear, I told you the heat flow area, this pi by 4 d square, remains constant. So heat is flowing from this surface and it is coming out from this surface. So during this distance, the heat is constant. Area is constant. Heat also constant. Now this week we are going to study radial. What is meant by radial? So in this plastic insulation, there is inside disc. The disc is look like a CD. Okay. So inside there is a hole and there is a heater. The heater is like this placed here. Heater. And this heater is connected with electric cable. Okay. And this heater will transfer. And now heat will flow. How heat will flow? Along the radial, along this direction, everywhere. See, if I consider this, the heat is flowing. Then later on, this area is increased. This area is increased. This area is increased. So what is the area? It is not a circular area, pi by 4 d square, no. How it is flowing? Along the circumference, 2 pi RL, 2 pi R. 2 pi R is perimeter and length is you can say thickness. So area is going to change as R is going to change. Area is going to change. So here now this is kept like this. So this is a hot heater. So here the temperature is more at radius 1. At radius 2, temperature is decreasing, decreasing, decreasing. So heat is flowing from all in radial direction. And we will see what is the relation between radius and temperature. So in objective, our first objective, we need to find out what is the temperature at radius R1, R2, R3, R4, R5 and the outer surface. We need to measure. So here there are 1, 2, 3, 4, 5, 6 thermocouples. Okay. So inside at the center there is a heater. Then this thermocouple number 1 is at a radius of 7 milli from the center. From the center 7 milli. Then second thermocouple is at a radius of 10 milli. Third 20, 30, 40, 50 and outer radius 55. So the diameter of disc is 110. So there are 6 thermocouples connected at 7, 10, 20, 30, 40, 50 and last is 55. There is no thermocouple. I need to find. So what is the temperature at the outer face? I can add one more objective there to find out the outer temperature. Okay. So if I know thermal conductivity, I can find out temperature. If I know temperature, I can find out thermal conductivity. So first objective, to find out temperature. I know temperature, I know radius, I know Q, I know area, I can find out thermal conductivity. If I know temperature, if I know Q, if I know thermal conductivity, I know last temperature, I can find out the outer temperature. Only one unknown. Okay. So our target, just write formula and put value, get answer. So what is the first steps? Make sure all the thermocouples connected to T1, T2. So can you see this number and tell me this number? What is this number?
1.
1. Is it connected to 1? See, this is 1 and
yes.
It is connected to 1. Next is a red color, 2. The red color is connected here, 2. Third is orange color, is connected to 3. Fourth is yellow color, is connected to 4th. Fifth is green color, connected to green color. And last is blue color, blue color. So make sure all the thermocouples are connected to respective thermocouple socket. Okay. Then start the water at a rate of 1.5 liter per minute approximately. So keep this, and this is 1.5 liter per minute, you can see. Okay, not more than, not less than, approximately a laminar flow. Okay, so Make sure all the setups, all the thermocouples are connected to respective socket. Number 2, start the water at a rate of 1.5 liter per minute. Make this switch, backside switch on. Make this all backside switches on. Okay. And now make switch on, main switch on. Yeah, there is no power. Yes, so make sure this is connected to. So I will make it off first from back and this. So make sure this is 110 or 120. Is it written here? What is written here? 220 volts. Okay, so I will connect this to 220 volt. Can you connect this there? So this is a new models, and it is 220, and these are the volts for 1 tap. Okay, now make this switch on. Then make this main switch on, and now adjust the voltage to 9 volt and 12 volt. So adjust this voltage. Come, adjust this voltage to 12 volt. Make sure though it is connected on voltage. Is it on voltage? Yes. So increase the voltage to 9 volt. Keep this temperature on T1, this on voltage, and increase the voltage to 9 volt. Wait for steady state to reach. Means there is no rise in temperature at least for 1 minute, and record the readings, and then increase the voltage to 12, and after 20 minutes take the readings. Okay, so we'll study the formulas and everything.
Experiment number 3. Title of the experiment is Radial Heat Conduction. Write the date, write the submission, write your ID, write your student name, team, lab section. We will move to our experiment. Objective of the experiment, I will explain it after the experimental description. So what is this radial heat conduction accessory? If you see from the top view, you can see the circular disc, and if you see from the side view, it is a rectangle. At the center there is a circular heater. So this is a heater. Heater is shown it here. Okay. So through which heat current is flowing. So this is a heater. And now 7 thermocouples are 7, 10, 20, 30, 40, 50, and last is. So these thermocouples you can see from here 1, 2, 3, 4, T1, T2, T3, T4, T5, T6. So here I will write the thermocouple T1 at radius of R1, T2 at radius of R2, then T6. So R1 is 7 milli, 10 milli, R2, then 20, R3, 30, R4, and outer radius is RO is 55 or diameter is 110. Now heat is flowing radially outward Q like this, heat is flowing like this, like this. The thickness of the plate is given to you. This is T is nothing but L is equal to 3.2 millimeter. So diameter of disc is 110 milli. So you can find RO is equal to 55 milli. Okay, so thickness is given and radius is given and thermocouple distance is given. So all these thermocouples. Now apply the Fourier's law. So Q is equal to Ka dt by T. So Q is constant here. K is thermal conductivity. It is a property of material. And here area. Area is 2 pi R L. Heat flow area. So this is 2 pi RL. So this is a thickness and heat is flowing across this. So perpendicular area is like this. If you see from 3D views like this, so this will be the perpendicular area. So heat is flowing like this direction outward. Okay. So area is 2 pi r L. So L is a constant, but R is varying from R1 to RO. So R is variable here. Area is not constant now. So this is not constant. Temperature is changing. And here X is nothing but R. So I will change this law as dt by dr. So what is dt by dr? If you consider a small elementary radius dr, this is dr. So what is the heat flowing in this direction and what is the temperature dt? And this is dr. So Fourier's law states that Q is equal to K 2 pi L R, I will consider small radius, and dt by dr. So this is Fourier's law of heat conduction for radial heat conduction. Now what is the variables here? Q is constant, K is constant, L is constant, R is variable, temperature is variable, radius is variable. So R is variable. Now I will take the terms, variable terms. Q is constant. So dr will come up here, dr, and this r will come down here. 1 by r is equal to K is constant, 2 pi, L is constant, and dt is variable. So if you integrate this equation from 1 to 2 to 2 to 3, or any point if you integrate from 1 to 2 or 2 to 3, so we'll get final equation. I will not show you the derivation. We will get the final equation. Q is equal to 2 pi L K T1 minus T2 divided by ln R2 by R1. So if you choose higher temperature minus lower temperature divided by higher radius divided by lower radius. So this is the formula for heat transfer. Now our objective is to find out thermal conductivity. So 2 minus 1, 1 minus 2. 3 by 1, 1 by 3, 1 minus 3. So this is our final equation. Now what is our objective? Our objective is to find out the temperature at various points and thermal conductivity of the material. Okay, and what is the effect of increasing the radius? What is the effect of increasing the radius on the temperature? So I can go back to objective and we will write the objectives. Number one objective, to find temperature distribution along radius of disk or cylinder. Number two, to find thermal conductivity of disk material. Number three, to find temperature at outer radius of disk. So these are the three objectives we can add to study the effect of temperature gradient along the radius. Now experimental procedure, as per the video you can write down the step-by-step procedure. And now observation. So observation means what is given to you. Number one, the diameter, the disk size is given to you. The diameter of the disk is the diameter of disk is 110 milli. Okay. Number two, the thickness of the disk is given. Thickness of disk is 3.2 milli. So you must convert it to meter. And number three, the distance of thermocouple from the center, the distance of distance of thermocouple couple the distance of thermocouples from center along along from center. The distance of thermocouple from center is 7 mm, 10 mm, 20 mm, 30 mm, 40 mm, and 50 mm. Now these are the observations given to you. Now observation table.
Yes. First voltage.
38.1.
Sorry, current. Yes.
1.5. No. T1 38.1. T2 36.2. T3 30.6. T4 29.0. T5 27.4. T6 26.3.
Back, keep it on T1 and voltage, and increase the voltage to 12 volt. So we'll wait for this 20 minutes.
So we will write the observation table for 9 volt. So first we adjusted the 9 volts, so we are going to measure current I, ampere. Then we are going to measure the temperature at various points, various radius. So first, temperature at R1 is equal to 7 milli, is equal to T1 degree centigrade. Temperature at R2 is equal to 10 milli, T2 degree centigrade. Temperature at R3 is equal to 20 milli, T3 degree centigrade. Temperature at R4 is equal to 30 milli, T4 degree centigrade. Temperature at R5 is equal to 40 milli, T5 degree centigrade. And temperature at R6 is equal to 50 milli, T6 degree centigrade. Now we'll record the readings for 9 volt. Okay, 9 volt. The current is 1.59, 38.1, 36.2, 30.2, 29.0, 27.4, 26.3, and for 12 volt, after 20 minutes waiting, we reached the steady state for 12 volt and we recorded the temperature, and it says 49.2. So there is no calculation table. Now our objective is to find out the thermal conductivity of the disk. So we need a voltage for the heat flow for that. So first we will write heat flow is equal to Q is equal to VI. Calculation for 9 volt, and you can complete that for 12 also. For heat flow is equal to 9 volt. 9 into 1.51 is equal to 14.31 watt. Thermal conductivity of disk is given by Fourier's law of conduction as Q is equal to the area 2 pi L K. So T1 minus T2 divided by ln R2 divided by R1. I can choose here 3, here 6. So I can choose here 6 and 3. So it is up to you to choose any number. Remember, higher minus lower divided by ln, higher divided by lower radius. I'll put the values, we'll get the thermal conductivity. So K is equal to the Q is millimeter or meter doesn't matter here, and T1 minus T2 is, you will get thermal conductivity K of is 133.6 watt per meter degree centigrade. So this is around the thermal conductivity of the brass. The material is brass as per the specification of the equipment. It is a brass and it is around same. So answer is correct. Okay, once I know the thermal conductivity, I can find out the temperature at outer radius. Number 3 for 9 volt. The temperature at outer radius in bracket R is equal to 55. RO is equal to 55 milli. So how I can find? Same formula I will use. Q is equal to 2 pi L K I know above T6 minus T0 outer surface divided by Ln RO divided by R6. So all the values I know, put the values. Q is equal to again 14.31 is equal to 2 pi L is 3.2 into 10 to the power minus 3. K is this 133.6 in bracket. So T6 is 26.3 minus I don't know T outer divided by Ln 55 divided by 50. If it is milli degree milli or meter doesn't matter. So solve this equation by equation solver, and we'll get T0 is equal to 25 by 8 should be less than T6. That's 26.3. So your answer is correct. So similarly, we can find out for 12 volt. Now graph, it is very important for us. The graph should be between temperature versus radius. So if you have this graph, you can use this graph or you can use the graph paper. If you use the graph paper, on x-axis 10 line is equal to 1 centimeter is equal to 10 into 10 to the power minus 3 meter. And on y-axis 10 line is equal to 1 centimeter is equal to 5 degrees centigrade. Okay, so we can choose the graph paper. This line as x-axis and y-axis on here as an y-axis. So this is our 0, this is 0, 10, 20, 30, 40, 50 plus 60. Last 55 point is here. Okay, so this is about, and now temperature. So I will start from 20, minimum temperature 25, then 30, 35, 40, 45, and 50 is the maximum temperature. So we can choose 50. So on x-axis is a temperature in degree centigrade, and right here radius in meter with the arrow, don't forget. Okay, now already we have the lines and we will plot the graph. Now first radius is 7, so I will mark here, then 10, 20, 30, 40, 50 and 55. The lines are there already. So for 7, now I can make the T1 also. It is there but no need. So another 20 here, 30, 40, T. There is no thermocouple, so we'll make it red. Now first temperature 38.1 we mark here. This is T1, T2, T3, T4, T5, T6, and this is TO. We don't have. First temperature is done. Now at 10 the temperature is 36.2, so 35, 36, yeah, then 30.2 for 20 radius, 30.2. So this is 30, 30.2. It is around, oh sorry, here. Next, at a radius 30, the temperature is 29, means 2 lines less here. Then 40, for 40 millimeter length, temperature is 74.5. So after 25, 26, 27 and a half line. So this is 27.5. Then at 50, 26 means two lines and it will. So join this by a smooth curve because it is a logarithmic curve. Better draw by a smooth curve passing through these points. Very smooth curve. It is a logarithmic, and from this point extend with the same slope. So we'll get this temperature and it is near about 25 degrees centigrade from graph. Okay. Similarly draw for 12 volt. The 49.2. So 45, 49 means two line less near about here. Okay. T2 is 45. So it is here. And extend it, and here we'll get T0. So this is 28 degrees centigrade for 12 volt, and this is 9 volt. Now it is important to get the slope of the curve in the review questions. So we'll go to the review questions. Now here we took a linear scale 0, 10, 20, 30. We can use also ln 10, ln 10. We can use logarithmic 20, 30, 40, 50, 60. And then we can find out the slope. So there are two methods. We can use linear, and then in slope we will use log. So what is asked now? First in review question, we need to find the slope at temperature gradient at 20, 30 and 40 for 9 volt, and 12 volt same procedure. So it is asked to find out the slope of the curve at 20. So I will draw the horizontal line, I will draw the vertical line. Okay, so this is dr and this is dt. So same at 30, so I can find out dt by dr. So this is nothing but t2 and this is nothing but t3. So t2 minus t3 divided by, so dt by dr at radius 20 is equal to t2 minus t3 divided by ln 20 minus 10, ln 20 minus ln 10. So similarly you can draw for here and here. Then again for 40 you can choose, you can draw vertical line and horizontal and vertical line. dt by dr at r is equal to 30 is equal to t3 minus t4 divided by ln 30 minus ln 20, ln 30 minus ln 20. So same way for dt by dr at r is equal to 40 is t4 minus t5 divided by ln ln 40 minus ln 30. So here you will get 20 is t2 is 36.2 minus 30.6 divided by ln 20 minus ln 10. So the answer will be 8.079 degrees centigrade per meter. So this is temperature, so you can put the values and similarly calculate that. Now similarly you can do for 12 volts. Now estimate the temperature at the periphery of the disk, 25 degrees centigrade and 28 degrees centigrade by. Now calculation. How to find by calculation? We calculated in calculation table. So at the radius of 55 milli by calculation is 25.8 degrees centigrade, and this calculate yourself. Now the last is conclusion. So very important conclusion. So first we need to write the relation between temperature and radius. Radius is a logarithmic. Number two, as heat flows towards outer radius temperature gradient dt by dr decreases. Okay. Number 3, the thermal conductivity of this material is K is equal to 133.6 watt per meter degree centigrade. And number 4, temperature at outer radius of disk is T0 is equal to 25 by graph and T0 is equal to 25.8 by calculation. So similarly, write down for 12 volt, write T0 is near about 20 degrees centigrade by graph and is equal to dash degree centigrade by calculation. You can add the thermal conductivity at 9 volt. So you can add the thermal conductivity. This is for 9 volt and you can add for 12 volt also. K is equal to dash watt per meter degree centigrade. So this is the end of the. Don't forget to clean the workbench.